Hello, my name is deGooyer. I'm a fourth-year electrical and computer engineering student at Dalhousie University.
Oh, I'm Amanda. I'm a chemical engineer. I graduated Dal this past May.
Cool. And today we're going to talk to you about just the design process. I think many people who are, especially in the engineering field here, have a general idea of the sort of strict design process that you go through. But I think the goal for today is to take a deeper look at some of the more important parts of the design process and how they can be applied to solving pretty much any problem that you have any day. So, how do I click to the next one?
Magic.
Magic, yeah.
See, as always. You can do
So,
it.
first thing we're going to do, we're going to talk about ourselves, who we are. Then we're going to go talk just a general idea of what the design process is. As we finish with that, we're going to give a little example as we go through as a group, step through all the different places of the design process. And then we're going to talk about some particular times we ourselves in industry have used the process, and then have a little Q&A discussion at the end with whatnot. So begin.
Okay, so when Jack and I decided to do a talk, we didn't really know what to do it on. And so we were trying to brainstorm ideas about, what do we have in common as people? And it turns out that while I clearly have so many excellent attributes, Jack's one good attribute is that he's tall and so he can reach things on top shelves. But we did find that we had one thing in common, that's we're both in engineering, or we're both engineers. And obviously we have a sense of humor, otherwise we wouldn't have put this excellent graphic up.
Sure.
So we decided to talk about design process, and Jack's going to walk us through just the actual kind of systematic way that engineers specifically use the design process, because everybody kind of has a version of it, but engineers were specifically very focused on going through it in a systematic way.
So here's the engineering design process. The first thing you do is you define the problem. Whatever the problem is, you hear it from someone else, you have to define it and do your background research sort of it to get an idea, sort of a sense and the context of the space that you're in. After you have a context, an idea of what sort of the project is, what the boundaries are, you need to actually specify the requirements. Now this might seem like a small step, but this is the most important one, because when you specify the requirements, those are going to be the ones that you're going to test your solution against. So whether it is, which we're going to get to our little project that we're going to talk about, it's very important that you specify the requirements just exactly that will fix the problem that you have. You then brainstorm, do your nice creative solution, whatever way you see fit, to figure out what would work. At which point then you'll develop a prototype and you'll test a solution. And the most important part that you have in the entire design process is here. This is what I think differs it from a lot of different processes, and really what makes the design process itself shine is that you test it against the requirements that you had at the beginning. So you look at exactly the requirements that you wrote, the numbers that you had, and if they meet the requirements that you have, then you continue. If not, you reiterate until you are completed. So you set out your requirements, you find what the project is, you set exactly what your requirements are, and then you meet to match those requirements. You try to shoot for more, but once you meet the requirements, you're done. You go on to the next project.
So instead of us just telling you this, because that's fun, we thought we might do an interactive scenario of the design process, because usually the best way to learn anything is through a nice example. So this is maybe not the best example, and I'm sure there's engineers in the room that could think of something better, but we thought this might be fun. So without further ado.
Step one, problem definition. So here's the problem statement that we are given. Poisonous snakes are a threat to the locals in Treasure Island. Each year, approximately 10 people die from snake bites. Snake bite is treatable, but only if the victim has access to the antivenom within 3 hours of being bitten. You are contacted by the Prime Minister of Treasure Island. She wants a system designed to deliver the antivenom to victims in the field. The island is 20 kilometers by 60 kilometers and has a variety of terrains and climates. Your task is to create a system to deliver the antivenom safely. Let's go. So that is the problem. It gives a lot of background and research, and from that, we must
define our requirements and constraints. So we have this problem. A client brings us a problem. Just in engineering speak, we often say, we have a client, they bring us a problem. But this is true of anybody doing any sort of problem solving. You always have a problem to start with, and then you kind of go through how to solve it. So we have our design / our client requirements. So the Prime Minister came to us, and she said, these are our requirements. So the antivenom has to be delivered within 3 hours. If it's not, then the person's going to die. So that's an absolute requirement that the design has to have. The antivenom has to be kept at a temperature of 10 degrees plus or minus 2 degrees. So we have some temperature control that we're required. The antivenom can't be overly agitated because it is a medication. It can only be held at the central hospital on the island. So we can't have satellite sites everywhere. Okay, we have one site in the center of the island. And the system cost can't exceed $50,000 because it's a small island, they don't have a huge budget, but there's an important problem that they want to solve. Okay?
Cool. So to reiterate again, this is probably the most important part of the design process, is when you break down a paragraph, people talking to actual testable criteria that you can do. So, what ideas do you have?
How might, this is interactive, so we want you guys to brainstorm some ideas of how you might go about solving this problem. How would you get the anti-venom in random locations that you don't know of, at any given moment in a day?
Come on.
Yes?
Just going by the non-agitation factor.
Yeah?
By air.
Sure. Okay, by air. So more specifically, do you have like a... Okay, a helicopter? Sure, that's a great idea. Yeah, no, that's fine. It's a good idea. We're just brainstorming at this point. Okay, drone. Anybody else have any other ones?
I was just going to second that. I was watching Kingsman last night, and they distributed the anti-whatever with the drone.
Excellent.
Drones cost between about $2,000 and $6,000, so it's quite actually affordable.
Yeah.
Excellent. Yes. A cannon. Okay, Brad has an idea. Vacuum tubes. An excellent system, and also perhaps mail delivery while we're at it. Okay, so.
Any other ideas, free proposal, anyone else?
All right. So, so we had some plants in the audience here, but so we're brainstorming ideas. Jack, you can go to the next one.
Cool.
So we actually are giving you some options because we're guiding this little endeavor.
Alright, so Humvee, obviously, because that seems like a pretty easy way to get stuff around. A cannon, because gotta get someplace point A to point B, you want to use a gun. And a drone, because, in theory.
And perhaps a carrier pigeon, but it's really like not the best option maybe, but potentially the best.
Cool.
We don't really know.
So now we gotta look at our options, and now, we don't have that much money. We need to go and narrow it down. So here are the pros and cons, the decision matrix that you made, something more complex if you're doing this in the field, but nevertheless, here is us comparing our options. On the first case, we have the Humvee here. It's pretty quick. It's not that fast, but it's not that good at traversing a bunch of different terrains. Some people might have a special training for it, but Humvee has training manuals for it. It's used in military settings, so if it breaks down, there should be 50 pages on how to fix it, no matter what breaks down on it. But it requires roads, right? The Humvee, and as much as they go all-terrain vehicle, it might not be that great. In the middle is the cannon, which is my personal favorite one. Treasure Island. There's probably one laying around that they could use. It's really quick. It's pretty cheap. But, there's a little bit of an issue with the fact that you're shooting a very delicate vial of venom, across an island, which might not really work that well. And finally, there's the drone. Pretty good speed to it. The one that we were looking at is quite fast. Whether that's the right speed or not, who knows?
It's our own drone.
Drone. $30,000 for development, training, whatnot. You can put a refrigeration system on it if you're, nice advanced like that. Surpass any terrain, but it has battery life, right? You don't want to be flying over someone's field and they shoot down with a shotgun, right? So you got to be really careful with the way the drone goes.
So we had a lot of pros and cons. We looked through our pros and cons, and we don't go through them all, but systematically we go through and we say, okay, how do all of these pros and cons meet our requirements and constraints? And you can see that based on our excellent list of random made-up stuff for our fictitious thing, we choose a solution, okay? And I love the drone idea. I really think that the drone, based on our list of things we made systematically, the drone is our best option. It can travel fast enough to get any point on the island. It costs less than $50,000, which is our budget, and that's a major constraint. Usually in most projects, time or money is a major constraint. We somehow have this refrigeration unit on it because it's our fictitious drone. And so, it can keep the vial at the appropriate temperature. And we also have this cool damper that I made up in my head that we installed on it. That means that it doesn't shake excessively. So, based on our requirements and constraints that we outlined at the beginning, which is really important to keep going back to all the time, the drone is an excellent option. So that's what we're going to choose. But
before we do that, we have to test it. So before you go and give your solution to someone else, you got to make sure it actually works. You can't just walk up to someone and say, here's the drone, you try it out, because that's how you get failures, engineering, disasters, and whatnot. So you have to test it. So we divide a series of tests, just 3 of them. You're gonna try, what happens at a mountain, use mountains at night. We use grassy fields in the middle of the day, or, swampland and a cyclone at dusk. You're gonna see what sort of different scenarios you can go through to test your device to see if it works. This might fall under validation, I believe, more
Yeah,
than verification.
yeah.
But you are trying to figure out, validation, you're trying to figure out if your drone will actually, work and fulfill the client requirements. So you run your test, you go through it.
So then we ask ourselves, does the solution meet our criteria? So have we met our requirements and constraints? So the first thing is that based on our testing, we found that victims actually had trouble locating the drone. So it was pretty accurate, but it wasn't always landing exactly where we needed it to. And they were having trouble locating the drone because of lack of light, or sometimes it was in tall grass, okay? So, even though it was landing really close to them, they were sometimes having trouble, maybe because, because of the venom, they're not thinking clearly. So the other thing is that the anti-venom must be kept at temperatures 10 degrees plus or minus 2, and we thought about that, and so we thought refrigeration unit, great, but then we didn't think about what if we run it at night and it's cold, and maybe it's actually too cold for the anti-venom. So we realized that we actually, we ran one trial at 0 degrees, and actually it got too cold. So not only, sometimes you think of, oh, well, usually it's hot, but sometimes there's always a factor that you're not really considering. So we have to deal with that. And then also, we said the anti-venom can't be overly agitated, and we did install that damper when it's kind of flying, but we didn't think of maybe when it lands, there might be problems with that, and so actually it fell off a mountain, because as it does, and the vial broke, so that didn't work. So based on our tests, we've now identified all these new problems that we maybe couldn't have conceptualized if we hadn't done that.
Cool. So from this, like we said, the goal of most engineering projects in order to design is to go back to your requirements. You take that problem statement, and you make your requirements. What we found is our thing did not work. And so you go back and you reiterate again. You find that you can put a lighting system on the drone so that people can see it at night or in tall grass or whatever, or some sort of location. But a heating and cooling system, make sure that it maintains temperature at the proper times, and a landing system so that it stabilizes when it's at the end, right? So what you do is you take the things that didn't work, and you try to fix the particular ones until you meet each of the requirements. And from that, you're able to do a final design which meets the objectives that you set out at the beginning and allows you to have add-ons, I believe.
Yeah. If we had to have add-ons for fixing these problems, asking yourself, do I still meet the budget constraint or the time constraint? Because eventually, the nice thing about engineering, the cool thing is that you're always considering that you don't have infinite time and you don't have infinite money. So you have to make the best design given those usually 2 really hard constraints.
Cool. All right, from that, we're just going to do a quick discussion, I think, of when we've actually put these in, use the design process.
Yeah, so I mean, it's great to talk about Treasure Island, and that's, it's a nice little activity, but how have we kind of used this in industry we thought might also be neat to talk about. So I'm going to talk about a project I did. So we have Haskap berries are full of antioxidants and other really important nutraceutical things. And as an engineer, you sometimes want to take kind of a raw material or waste material, and from that, be able to design a process to get the maximum amount of stuff out of your waste material, right? It's called waste valorization. So I did a project looking at taking Haskap berries and Haskap waste and trying to get stuff out of it that could be used in nutraceutical applications. So in order to do that, we actually go through the design process very systematically. So you start by, doing background research. What can I even get out of this waste that I have? And from that, start designing an experiment. And you do a preliminary design and you iterate. You do the first thing after you've made your requirements and you see maybe it doesn't meet the requirements. So you keep going and you keep going and you keep going. And then you get to a point where you really understand your system. And that's that cyclical nature. You finally understand your system. And then you might even go so far as to do an optimization of your system. So you take your system and you say, now I want to obviously get the maximum amount. So I have a threshold, but I want the maximum amount. And you can actually make 3D plots of your extraction parameters and look at how different things will affect your overall extraction. And when you're using the design process, what's good is you're getting a good large picture of how everything is going. And so that's what I did. So these surface plots basically represent how I can get the maximum amount of stuff out of my Haskap berries given different parameters. And so I iterated, I think this is like my 3rd iteration of my surface plots, basically trying to figure out what the maximum amount that I could get out given my constraints and everything like that. So it was actually a very simple but rigorous application of the design process.
Cool. And so what I have here is my design for multi-channel 6 GHz zero field USR spectrometer. I designed this when I was working at Triumph over the winter semester at UBC. Effectively, the nuance spectrometer is able to deduce the intrinsic magnetic fields of sort of advanced materials. I can go through the whole process of it, but effectively I took this very, very physics-heavy bounded device and came to the point that all my job was, the engineer, and what I was trying to optimize, was that a positron would come up, it would hit one of these light-emitting bars, travel on the light-emitting bars to the sides, and you'd have to try to pinpoint the time and the location of where that happened. So effectively I had to design a system that detected positrons and their hit location. So I went through the entire process. I found my requirements. The timing resolution, I think, for 6 GHz is 120 nanoseconds.
That sounds right. I have no
120
idea.
Picoseconds, I believe. So very fast electronics. Had to go through all the process of it. But once I had my design constraints, I just kept on reiterating again and again. So what you can see here, actually, on this design is here are the light scintillators, which is where the light kind of came from. And on the sides, on both sides, are PCBs that just detect the light. And you can actually see two different widths that are on here. We were trying to cut costs because each of these different PCBs cost like $500 each. They're not really what you want to put 180 of them on, which is the final design. So instead, we're testing to see that if we just make the bars a little bit wider, how much worse was our timing resolution for it? So that right there is one of the configurations. This is the full configuration, but a lesser configuration would just have one PCB on each side. And so we're testing this to get our costs down and see if they still meet the requirements that we wanted to have, which was around 60 GHz for the resolution. But yeah, that's an example that I have personally of, take a really complex thing like a physics problem like that, break it to something simple and just try to solve that problem, not the whole world.
So our conclusion. So cyclical things are everywhere. So we just pulled up a few quick ones. Apparently, people that write, I don't know how to do that, but others do, use a cycle. And management also don't know how to do that, use a cycle. And software development also uses a cycle. So you can see that cycles are everywhere. It's really good because we should be learning all the time from what we're doing. And so we as engineers, because we usually don't know how to talk about much else, but we thought it would be cool to talk about the design process because you can all use it in anything that you're doing. So even if you're designing, if you're doing a leadership conference or something like that, the design process is actually applicable. And if you look through all the different things, you can see how that might happen. If every year you're doing a leadership conference, iterating, always learning from what you're doing, implementing new things, trying new things, doing test runs, doing small scale things all the time, help you to kind of build a network that helps you, produce a better final product and helps you kind of continuously learn and grow and improve.
Yeah.
So that's our conclusion, and we'll take any questions if you have them. Yes, Wesley.
What's the main difference between validation and verification?
So verification has to do with your internal engineering requirements, right? So like when you have, for example here, we kind of mixed up validation and verification for a lot of the stuff, but a engineering requirement is a numerical number, so plus or minus 2 degrees centigrade. So a verification process would be, does your thing stay between those two numbers? Whereas a validation process is more so a test in the field. So like if you are going and you fly it out and it stays at the right temperature, that'd be validation of your system, whereas verification of your system is did it stay between the temperature things and the control environment. Yeah. Got a whole class on that.
Cool.
Any other questions?
Yes, Wesley.
Did you both of you sort of learn a lot of this from your experience, like the experiences that you shared, or did you actually learn a lot about it in school?
So I can kind of speak to that. So I found we touched on it a lot in school, and then when I went into kind of the field and worked in different places, I think it was kind of like expected that we knew how to use this and implement it. And it wasn't actually until my final year of engineering that we were kind of put through a kind of rigorous test of, do you actually know how to implement this and know how to use it. And actually, when you sit down to try and use it, it's much more difficult than it seems, because it seems like you just follow a flow chart. But yeah, I found that obviously the best way to learn it is to implement it in a real situation. But I found it was almost an expectation as an engineering student that was something you inherently knew how to do. So yeah, I don't know about you.
For me, it was a lot of classroom stuff to begin with, but I found that when I actually had like time on the job, knowing the design process helped me a lot, because if not, you would have no idea how to do anything. You'd be stuck in the weeds. But if you make the requirements you want, you just get through it.
Yeah.
It takes time.
It saves a lot of time for sure.
A lot of time.
Cool.
Brad, no questions?
Come on, Brad.
Bad.
I think I'm good.
Are you sure? Oh, he seems, yeah.
All right.
Awesome.
Thank you, guys.
All right, thanks, guys.